A conservative vector field is defined to be one for which there exists a function little f such that the field is the gradient of that little f. So a conservative vector field is a field big F of whatever the variables are. This can apply to any number of dimensions. So big F is a vector field defined at all points and within some region. And I'm being vague about region and so forth, simply connected regions, etc. Again, trying to get the basic fundamental idea across, but there are conditions we got to think about, but we're not going to think about those too much right now. So again, a vector function defined at every point within some region of some multidimensional space, which is equal to the gradient of some other function that's also defined within that space. Okay. Now, if there is such a function, then little f, the function of which we take the gradient, is called the scalar potential function for the vector field f, the field which is the gradient of that scalar potential function. One example, if you're familiar with physics, and I think we've probably referred to this a couple of times, is where the vector field is the gravitational field of some planet or astronomical object. It doesn't have to be that large, but to get a significant field, it usually is. So if f is a scalar potential function for the vector field f, then if f is the gravitational field, f is the potential energy function. Many other examples, and we'll talk about those later. So there are several conditions that are met by a conservative field and several alternative possible definitions of a conservative field, several conditions that are equivalent to a vector field being conservative. So first of all, if f is conservative, then it follows, as we've just seen, that the integral over any closed curve of f dot ds is just f of q minus f of p, where q is the one endpoint of the curve and p is the other endpoint, p being the initial point, q being the terminal point. There's another statement we can make that's converse to this, showing that these two conditions are actually equivalent in a sense. And the condition is simply that if this is true for all closed curves, and that's a closed curve, not a closed curve, closed curve. If this is true for all closed curves within our vaguely defined region, then the function is conservative. So in other words, if you can always do this, the function is conservative, and I can even define the function. If this condition holds, then let's say A be any point within the region and define f at point B to be f of B equals, I'm being careless with my notation, let me fix this. Okay, we're talking about the scalar function. So that f of B is going to equal the integral over a closed curve of f dot ds where C is a curve or a path from A to B. If we understand what this means, if we understand these integrals and definitions, then it's easy to verify that this function defined by this integral is first of all well defined, and second that it satisfies this condition. So that if we know the function little f, we can always integrate the function big F. And if we know the function big F, we can use it to always define the function little f. I'll mention that this function is defined in such a way that little f evaluated at a is 0, since little f at a would be the integral over a curve that goes from a to a. Since the curve ends up in the same point where it starts, then this integral has to be 0. We could add an arbitrary constant to this result, so that for every point B we add the same arbitrary constant, and we would still get a function that satisfies these conditions. So that in this sense, big F can be defined as the gradient of little f, or little f can be defined as an integral of big F, in complete analogy with the fundamental theorem. Now there's another condition. That is that function f is conservative if and only if, meaning that f being conservative is equivalent to this condition. F is conservative if and only if the integral over any closed curve of f dot ds equals 0. And the basic picture corresponding to this is simply we have a point P. We've already seen this picture, a point P and a point Q. We have one path from P to Q, and we have another path from P to Q. So that the integral over a closed path of f dot ds could be the integral over path 1 of f dot ds. So, for example, path 1 from P to Q minus the integral over path 2 of f dot ds, and that would be the integral from Q to P, which would equal little f at Q minus little f at P. First integral, path 1, we go from P to Q. Second path, we go from Q to P, so that the integral over that path has to be f of P minus f of Q, which equals, and we have f of Q here minus negative f of Q here, and I've been careless in writing down my sign. It would be f of the integral over path 1 plus the integral over path 2, and we're going to define path 1 as going in this direction and path 2 as going in this direction, so that we would be adding those two paths. And in this case, we see that the f of Q and the minus f of Q, the negative f of P and the positive f of P add up to 0. This argument shows that if f is conservative, then this condition has to hold, because we can take any closed curve and put a point P at one point on the curve and a point Q at another point on the curve, and construct this pair of integrals that have to add up to 0. Conversely, we can argue that if the integral over any closed path is 0, then whatever our points P and Q, we can put them in the middle of some closed path that has these properties showing that f must be conservative. Now I've left some details out of this argument that this implies this. I expect you to be able to fill in those details, and I've left out some details in this argument as well, but you get the gist of both arguments. This argument saying that f is conservative if and only if the integral over any closed path is 0. And this one saying that f is conservative if and only if the integral over any closed curve of f dot ds equals f of q minus f of p. And that's this argument here. And I'm not sure that even shows. So let's move over though. Okay, again, this pair of statements here says that f is conservative if and only if this condition holds.